Today we're talking about rhombuses, rectangles, and squares, and I'm doing kind of a funny order, so pay attention. I'm going to talk about rectangles first. The definition of a rectangle is that it has to have 4 right angles. So that's going to be our first property. And let's mark that on our picture, 4 right angles. This probably won't surprise you, but rectangles are considered a lot when you're talking construction. So I want you to see this little video about how they use the property of a rectangle to make sure a door is set up right.
Hello, my name is Rhonda, and today we are going to show you how to determine if your door is plumb, level, and square. First, we'll check to see if the unit is plumb. A unit is plumb when both the lock side and the hinge side jambs have true vertical alignment. To check to see if the head jamb is level, hold a 2-foot level flat against the top jamb. Check to see if the bubble is centered between the 2 lines on the vial. If it is, then the head jamb is level. Finally, square is when all 4 corners are at perfect right angles. To determine if your door unit is square, you will need a tape measure that is at least 10 feet long, and you will probably need 2 people for this test. Start by holding the end of the tape measure where the sill and side jamb meet. Run the tape measure up to the opposite top corner where the side jamb meets the head jamb. Pull the tape measure tight and record the measurement. Starting at the opposite corners, take a second measurement from corner to corner and note the measurement. If the 2 measurements are the same, the unit is square. If they are not the same, you may experience some operational issues with the door, such as the door sticking on the jamb. We have now successfully demonstrated how to check a unit for plumb, level, and square.
So that technique is going to be our second property of rectangles, the fact that the crisscross measurements have to be the same. We call those the diagonals again. The diagonals are congruent. It's a little bit hard to mark that because they crisscross each other, so maybe tick, tick. Would you know that that means that those entire diagonals are congruent to each other? But now property number 3 brings up another point. Did you know that a rectangle is technically a parallelogram? Because it fits the definition of a parallelogram. Parallelograms have to have opposite sides parallel, both pairs of opposite sides parallel. And those 90-degree angles in the corners force the sides to be parallel. So a rectangle inherits all the properties of a parallelogram. Just a quick run through of those properties again. Remember that opposite sides are congruent on a parallelogram, and opposite angles are congruent on a parallelogram, which obviously they're all 90s, so they're going to be congruent. We have consecutive angles are supplementary. Well, if you have 90s, 90 plus 90 equals 180, so there's no problem there. And also the fact that the diagonals bisect each other. So we know that our diagonals are actually the same length in a rectangle, but they also cut each other into equal pieces. Let's try an example on a rectangle problem. This is 5, 6, 7, and 8 from the sheet that I gave you. It says that this is a rectangle and the diagonals intersect at point T. Given that the measure of RPS, angle RPS, that's this angle right here, is 59 degrees, and the length of Q to S is 24, find the indicated measure. The first thing they're asking for is the measure of angle QPR. QPR is right here. And we know that those 2 angles together have to make that 90-degree angle since there's a rectangle. So 90 minus 59 is 31. How about angle PTQ? This angle right here. I didn't hear anything about how the diagonals crossed each other. However, if you see the triangle here, triangle PTQ, and the fact that these rectangles are going to have so much symmetry, we're going to be able to use that triangle. In fact, angle PQS up here is going to have to be 31 degrees. And you could kind of prove that to yourself by considering that alternate interior angles have to be congruent to one another. So all of those angles wind up matching up. So back to that triangle has to add up to 180 with all those angles all together. So far I've got 31 plus 31, that's 62 degrees. So that leaves me with how much for that blue angle in the middle? 180 minus 62 is 118 degrees. All right, the length of ST. I don't know if you remember, but remember that 24? Remember, all the way from Q to S was 24. And since this rectangle inherited all those parallelogram properties, that 24 has to be split equally. Remember, the diagonals bisect each other for parallelograms. So if you split that 24 equally, each piece would be 12, so the length of segment ST is 12. What does that mean for PR? PR is the other diagonal, and we just learned that just for rectangles have a property that their diagonals are congruent. So if QS was 24, then PR is also 24, and also would be split 12 and 12. So much symmetry going on in a rectangle. We're going to go to the rhombus next. A rhombus is simply a four-sided shape where all four sides are congruent. So that'll be property number one, the definition, four congruent sides. So it's almost like a square that's kind of leaning over. And maybe you guessed, can you tell that it really looks like a parallelogram? It just happens to have four congruent sides. So I'm going to do a spoiler alert. Property number 4 is that this thing is going to inherit all the properties of a parallelogram too. Properties 2 and 3 are both about the diagonals. So those lines that crisscross in the center, actually the point where they crisscross, again, that's going to be the midpoint because it's inheriting everything from the parallelogram properties. But not only is it just a midpoint, they actually cross each other in a certain way. Do you notice anything about how they're crossing in here? Isn't that a nice little intersection? Well, it turns out that those diagonals are perpendicular to each other. We actually get to play with 4 little right triangles in here. That's fun. One other thing about the diagonals is how they meet the corners. Do you see how those diagonals are coming into those vertices? Well, it's about the angles in there. Do you see how this angle right here looks obtuse? But do you see how nicely it's split by that diagonal? What do we call it when a line splits an angle into 2 equal pieces? We call that an angle bisector. And it turns out that all 4 angles get split into equal parts by those diagonals. That doesn't happen on parallelograms. That doesn't happen on rectangles. That's a special property just for rhombuses. The diagonals bisect each other, but the diagonals also bisect the angles. As in bisect the angles of the rhombus. Those 4 rhombus angles get cut into 2 equal pieces. And then of course adding the fact that we've got those parallels, the opposite sides congruent, obviously, because they're all congruent. The opposite angles congruent, because they get those parallelogram properties. Because of those parallels, we're going to have those supplementary angles. The x plus the y always has to be 180. And on top of that, those diagonals, when you draw them in, they bisect each other, which means the lengths are the same. Remember that this whole bisect the angles thing means the angle measures are the same, where bisect each other means the lengths are the same, like on a ruler. I've got a nice rhombus example here, but some of the letters are missing. That was on purpose. The diagonals of rhombus, W, X, Y, Z. I just wanted to point out that those letters always have to go in order. W, X, so the Y has to be this one and the Z has to be right here. And in the instructions, it also tells us that those diagonals intersect at point V. Now we know where the letters are. It also tells us that the measure of XZY is 42 degrees. XZY is 42 degrees. And the length of WV is 5. And maybe we can just fill in a few things right away, just the obvious things. See how that 42 degrees down there? This is going to have to be 42 degrees as well because of that property that the diagonals bisect the angles of the rhombus. And that 5 up there from W to V means that it's going to also be 5 from V to Y because the diagonals bisect each other lengthwise because of that parallelogram property. So number 1 is asking us the measure of WZV, angle WZV, and that was that 42 we just talked about. The diagonals bisecting those angles. The measure of angle XYZ. XYZ is this big angle right here. I'm going to use another parallelogram property to figure that out. I know that this entire angle is 84 degrees, right? And we know that consecutive angles for parallelograms have to be supplementary. So this angle over here is going to have to add up to 84 to make 180. What would that be? Is that 96 degrees? So that's a 96 degree angle in there. And then you know what? We could even divide that by 2 to find out how big each of these angles are. But then they asked me for the length of WY. Well, we already know that. W to Y would just be 5 plus 5. This last one's where it gets fun. We want to find the length of XY. That's the side of the rhombus. If they would have given me any side of that rhombus, I could have told you right away what that length is, but I don't know any of those sides. But remember how excited I was about the fact that we had those right angles where the diagonals intersected? The reason that's good news for us is because we have beautiful little right triangles in there. And I'm actually going to use that right triangle to try to figure out how long side XY is. I think I'm going to label it with a C since it's the hypotenuse of that little right triangle. And actually, if I knew this side, I would probably just use the Pythagorean theorem to find that hypotenuse, right? But I don't know that side, so I'm going to wind up using SOHCAHTOA. So I will want to do that 96 degree angle divided into 2 equal pieces would make this a little 48 and this a little 48 because the diagonals bisect the angles. Why don't I draw that green triangle out separately, just to make it a little bit easier to see. So I do know that that length was 5 from V to Y. And I know that this angle right here is a 48 degree angle. Do you see how I can use SOHCAHTOA to find the length of C? I've got the adjacent side over here, and I'm looking for the hypotenuse. Adjacent hypotenuse, that's a cosine. Cosine of 48 degrees is equal to adjacent over hypotenuse. Gonna have to cross multiply. And so C is going to wind up being 5 divided by cosine of 48, which isn't a whole number, but it's about 7.47. So the length of XY is about 7.47. And our last quadrilateral of the day is the square. The definition of a square is 4 right angles, 4 congruent sides. And go ahead and mark that on the picture. Hey, doesn't a rhombus have 4 congruent sides? Hey, doesn't a rectangle have 4 right angles? You might have guessed that the square actually inherits all the properties of a rhombus and a rectangle. That's what we're going to call properties 2 and 3. The square inherits all the rectangle properties because of those 4 right angles. And in particular, I'm just going to mention that one new property for rectangles, that the diagonals are congruent to each other. You wouldn't have to write that down because you've got your properties of rectangles right there. And then a square gets all those rhombus properties because it fits the definition of a rhombus, the fact that the 4 sides are congruent. And so those diagonal properties about rhombuses work for squares too. Remember, the diagonals are perpendicular and they cut those angles in half. Again, you wouldn't have to write that down because you have those to reference right there, but knowing that those angles are cut in half is kind of nice because 90 degree angles cut in half, we know that those are all going to make nice little 45 degree angles. And on top of that, we've got these crossing perpendicularly. So do you know what we have here? Little 45, 45, 90 triangles all over the place. And then the final square property is just the fact that a square is a parallelogram. Its sides are parallel, right? So it also inherits all 5 parallelogram properties. Let's do a little example. Here we've got the diagonals intersecting at J, and given that GJ is 7, find the indicated measures. The first one we want to find is angle EJF. How big would angle EJF be? The right answer is that it's a right angle. Remember that that's a rhombus property. The diagonals are perpendicular, so angle EJF has to be 90 degrees. How about angle JFG? JFG, that would be this one up here. And I kind of mentioned it before because this has to be a 90-degree angle because it's a square, and the diagonal splits that because of that rhombus property. Each of these is a 45-degree angle. 90 divided by 2 is 45. How long do you suppose it is from F to H? F to H. So what about the lengths of the diagonals? I know that that little chunk down there is 7, so this top chunk must be 7. And since the square is a special type of rectangle, this length and this length have to match. So these are both 7s as well, and from F to H, that total distance is 14. And I guess we kind of already answered the last one too, from E to J. Because the diagonals bisect each other, that was the parallelogram property, E to J would be 7. Now I did want to mention, just because I can, we've got these 45, 45, 90 triangles in there, right? Do you remember how long FG would be? If this is 7 and this is 7, and that's a 45, 45, 90 triangle, this is the hypotenuse. It would be 7 times the square root of 2. So we actually know the length of all the sides of this square too. You might be tired of this video, but you're going to have to do some of these problems on your homework today, so it's worth staying tuned. This one says, for any rhombus ABCD, your best bet is to draw yourself the nicest rhombus you can and label those vertices A, B, C, D in that order. That'll help you answer these questions. And now we're going to try to answer if this is always or sometimes true. Angle ABC, that's this angle right here, and angle CDA, that's this angle right here. Are those always congruent on a rhombus? And I would say yes, they have to be. Whose property is that the opposite angles have to be congruent? That was a parallelogram property. So I know that that would always be true. And how about the next one? Segment CA congruent to segment DB. Segment CA congruent to segment DB. Oh, they're talking about the diagonals. Are the diagonals congruent? Well, honestly, when I look at this picture, it doesn't look like it. Do you see how AC looks shorter than BD? So I don't think that's always true. Would it be sometimes true? The diagonals being congruent, isn't that a rectangle property? But guess what? If you have made that rhombus stand nice and tall, if you made that rhombus stand up straight, we'd probably call it a square then, right? But remember that a square is a special type of rhombus since it has 4 congruent sides. So it is possible for a special type of rhombus to have congruent diagonals. So I just drew 2 rhombuses, one rhombusy and one looking more like a square, where one of them has congruent diagonals but the other one does not. And so this would be a sometimes true. And the special case, when it is sometimes true, I could say if the rhombus is a square. Because if it's a square, then it is going to inherit all those rectangle properties. This next one is about a rectangle, FGHJ. I found the more carefully I can draw these, the easier these questions are to answer. Decide whether this is always or sometimes true. Angle F congruent to angle H. That is a for sure, because all 4 angles are right angles on a rectangle. Next question, would side GH have to be congruent to side HJ? The way that I drew this rectangle, it looks like HJ is a little bit longer, doesn't it? So it's definitely not an always. Rectangles can be longer than they are tall, but I bet it's a sometimes. What type of rectangle would have it where the GH and the HJ were congruent? Remember that a rectangle just has to have 4 right angles. So if I draw this rectangle looking like a square, then I would have segment GH congruent to segment HJ. So the only time that that would be true is if your rectangle were square-shaped. When it asks us to classify a quadrilateral, it wants us to get as specific as possible. I like to start at the top and work my way down. So when I look at this first one, it looks like a square, honestly. I see that the opposite sides are congruent. Opposite sides congruent is a parallelogram property. But actually all 4 sides are congruent, so that makes it even more special. That makes it a rhombus, right? With 4 congruent sides. I've got some right angles going on here, and since I already know it's a parallelogram, I know that the opposite angles have to be congruent. So it turns out all of these are going to have to be right angles. So 4 right angles makes something a rectangle too. But now even more specifically, 4 right angles and 4 congruent sides, that's a square. So if it asked me to classify this quadrilateral, I would classify it as specifically as I could, as far down the food chain as I could. I would call this a square, and my explanation would be that it has 4 right angles and 4 congruent sides. This next one starts off really similarly, right? Opposite sides are congruent, making it a parallelogram. All 4 sides are congruent, in fact, which means it's a rhombus. Because it's a parallelogram, those opposite angles are congruent, and the consecutive angles are supplementary. But from that, I can tell that this can't be a rectangle. It doesn't have 4 right angles. And if it doesn't have 4 right angles, it also can't be a square. So the most specific I could get on this one was I can call it a rhombus because it has 4 congruent sides, but not 4 right angles.